for showing up tonight. My name is Steve Rowley. I'm the current chairman for the Montana section of the American Chemical Society.
Super loud, Steve.
Oh boy. I'm not good at talking loud, but I'll do it. Anyway, thank you for coming tonight. The whole purpose of this event is that the American Chemical Society, we currently have a challenge, especially in Montana. Our section is very large. It covers the entire state of Montana. And it's hard for us to meet sometimes because we're asking graduate students or undergraduate students to commute across the entire state, oftentimes in the winter when the weather's bad, for us to meet. And what we've done to combat this challenge is we've partnered with a few entities here in Missoula, and here in Montana anyway, to allow us to kind of convey our message across the state and be able to meet in a interactive way across long distances. So you may see some cameras here tonight. I'm sorry if your camera's shy. Just tell them I don't want to be on camera, no problem. But we're filming this event, and the reason for that is that we would like to share this information across the state. So we plan to produce this professionally and make it available on our social media sites. And in order to do that, we've partnered with a Missoula company here called Inspired Classroom. And Inspired Classroom is a company that specializes in providing content for teaching, for educational purposes. And they're able to help people, students across the state, learn and in an interactive way without actually having to travel here. So we've partnered with them. We've also partnered with Midland Scientific, which is a distributor of chemical products here in Montana, and they've sponsored this event. So I'd like to thank Midland Scientific for that contribution tonight to make this available, to make this possible. Before we get involved, I just want to get a little bit philosophical with you, if you will indulge me for a moment. I want to talk to you about the field of chemistry, which is my passion, and tell you why I enjoy this so much. When I was a child, you know, my grandfather actually was the biggest influence on my life, and he was a polymers chemist. He worked for ExxonMobil and a little company called Polychrome. And he helped pioneer the field of polymer chemistry. And when I was young, I remember him talking to me about science in general. And one of the things he told me is, Steve, none of us, no chemist alive, today or ever, has ever seen an atom with our eyes. We've never seen a molecule with our eyes. And the reason for that is that you can fit 1,000 atoms within the amount of space that a single wavelength of visible light occupies. And to me, that means that we will never be able to see atoms. We'll never be able to see them unless the fundamentals of the electromagnetic spectrum somehow changes. We will never be able to see this with our eyes. And we live in a world today where seeing is believing. And the concept of seeing things with our eyes plays a big role in shaping how we perceive reality. And in the field of chemistry, none of us have been able to see the product of our work with our eyes. Yet, despite all of this, we're able to manipulate atoms. We can identify molecules. We've elucidated many of the mysteries of how they work to the point that we can manipulate them to our bidding, to the end of creating novel molecules to cure disease, to treat disease, to build polymers that help us develop consumer products, to improve the performance of batteries and electronics, And we do all of this without ever actually being able to see the product of our work. And in my mind, that means that chemistry as a field has gone a long way in helping us understand the concept of reality and how we perceive reality. And seeing is not necessarily believing, and in fact, in most areas of modern science, seeing is neither necessary nor sufficient to create belief. And in the field of chemistry, we are not able to do any of these things, creating new molecules, creating new materials. We're not able to do any of these things without being able to see the unseeable. And there's a whole field within chemistry, it's known as analytical chemistry, where they have been able to help us see the unseeable. Basically through the art of manipulating the electromagnetic spectrum so that we can visualize the unseeable. And that has nothing to do with beer. We're here to talk about beer, but it actually has a lot to do with beer. And with that, I want to introduce our guest, Dr. Chris Palmer, who has devoted his life to helping us see the unseeable. Dr. Chris Palmer, he's an analytical chemist who has devoted his life to manipulating the electromagnetic spectrum and other techniques throughout the field of chemistry to help all of the other chemists build molecules and improve our products and make things even as trivial as beer much better. So I also want to talk about, like I said, the purpose that we're here is to kind of engage the community. The Montana section of the American Chemical Society would like to engage the community in many ways, and beer brewing seemed like an obvious first start for how we can kind of reach out. But we are launching a program starting tonight where we would like to invite folks like Dr. Palmer to engage the community and offer a chemist's perspective on things that matter to all of us. And it doesn't just have to be beer, it can be environmental aspects, it can be political aspects, whatever. So I would encourage all of you to come talk to me throughout the night if you have anything on your mind that you would like to hear a chemist address. I would like to know about it because we have a few more events like this coming up throughout the year. With that being said, I'd like to introduce Dr. Palmer. He is a professor of analytical chemistry at the University of Montana. He's traveled the world taking measurements in chemistry, which is of course important, but also tasting beer. He's been at the University of Montana since 2001. He received his PhD in analytical chemistry from the University of Arizona. And he has worked not only in academia, but in industry through companies like Unilever. He's been in the Netherlands, he's been in Japan, he's been in New Mexico, Sao Paulo, all of these places taking measurements and helping chemists see the unseeable. And I'm hoping that tonight he can help us see what is unseeable in the art of brewing beer.
Great. Thanks, Steve. It's kind of a hard act to follow, actually. Cheers. So, yeah, I have traveled around quite a bit and tasted a lot of different styles of beer, and I've spent a lot of time studying chemistry as well. I am not a beer chemist. I'm not somebody who's spent his life studying the chemistry of beer, but I have an interest in beer, as many of us do, I think, in this room. And I also have an interest in chemistry, so I've kind of put those two things together and spent some time learning a little bit about what's behind the chemistry of brewing. So I want to thank Steve for putting this together and the Montana ACS. I think, Steve, you got a grant to put several of these talks together for the community. There seems to be quite a bit of community interest here tonight. That's great. Good to see. It's great to see a lot of familiar faces here in the room, and look forward to visiting with you after the talk. So other people, Great Burn obviously hosting this event, and great folks here and really great beer here as well. Midland Scientific, Todd is back there somewhere. There he is. He's the most important person here, not me, because he's giving out the tickets for free beer. And then Inspired Classroom here in Missoula is a company that's putting together a lot of different types of presentations and things for electronic presentations and so forth. People have asked me about the title of this talk, Great Beer Makes for Great Chemistry. Obviously there's a lot of great chemistry in beer, and so you could have put it the other way, great chemistry makes for great beer. But as it turns out, there's been a lot of great chemists who have worked for brewers, and they've done a lot of great chemistry over the years as well. So the brewing industry has really fostered a lot of the really interesting chemistry, a lot of the remarkable chemistry that we talk about all the time in class. For example, the pH scale, I don't know if people know this, but the pH scale was developed by a chemist at Carlsberg Brewing Company. So there's a lot of different connections back to beer because there's a lot of chemistry involved in brewing beer. And so there's been a lot of chemists involved in this industry over the years, and they've developed a lot of really interesting chemistry. The other thing is that just drinking great beer together with a group of people like this makes for great chemistry among the people as well. So I like that. So pretty much everybody in this room, I assume, already knows this first bit of information about beer. But beer is made from 4 essential ingredients. And those 4 essential ingredients are grain of some kind, almost always barley, malted barley. And that's the source of sugars, but it's also a source of proteins and enzymes that are necessary to be able to brew the beer. And then we have water, and water is perhaps the most simple molecule you can imagine, H2O. It's not the water that we're interested in, but it's all the other small, low concentration components that are dissolved in the water that make a big difference in terms of the beer. And then there's hops, and hops add bitterness to the beer. Hops cut the sweetness of the beer so that we enjoy it more. They provide aroma for the beer. And not everybody knows they're antimicrobial as well, so that if you have other microbes that somehow make it into your beer, they will help to preserve the beer and prevent it from going bad while it's in storage. And then yeast. Yeast is the hero of this story, and we're going to talk a lot about yeast. But yeast is what generates the ethanol. So we start with the sugar from the malted barley, and through fermentation, yeast produces the ethanol, which makes for the great chemistry, as I talked about just a moment ago. So the basic chemical process is we have sugar. Sugar comes from the barley, from the malted barley. We add yeast. The yeast acts on the sugar through fermentation to produce alcohol and carbon dioxide. And chemists, we have a way of representing things beyond just the text. So the sugar is a combination of carbon, hydrogen, and oxygen. 6 carbons in the sugar that we're interested in, 12 hydrogens, and 6 oxygens combined together to make a molecule of glucose. That plus the yeast produce the ethanol that we're also interested in, and the carbon dioxide, which is what gives the carbonation to the beer, right? Yeast does this not because it's doing it out of kindness to us to produce the ethanol. The yeast does this because it's generating energy for itself. And students of biochemistry will understand when I say that the yeast is able to store a certain amount of energy in the molecule ATP, and it's just 2 molecules of ATP per sugar molecule. And if you were to compare that with respiration, which is what all of us in this room are doing right now, where we take sugar plus oxygen, the oxygen in the air, and we combine that to form water and carbon dioxide. Okay? Same basic idea, we're metabolizing that sugar to generate energy for ourselves, but we're generating 28 molecules of ATP, so more than 10 times as many molecules, almost 15 times as much energy is stored when we use sugar through respiration. And it turns out yeast can do the same thing. Yeast can also use oxygen and sugar through respiration to form water and carbon dioxide. But fortunately for us, yeast doesn't do that in this process for two reasons. One is, when there's a lot of sugar around, yeast actually prefers to generate ethanol as opposed to generating carbon dioxide and water. And it does that, nobody knows really why. It's not a conscious decision, it's not a conscious being. But it does generate the ethanol in part perhaps because that gives it a competitive advantage against other microbes that aren't so stable in the presence of ethanol. All right. The other thing is that most of the brewing process, most of the fermentation process is done in the absence of oxygen. So we don't have oxygen around. Yeast doesn't have oxygen to go through this respiration process, so it's forced to go through this fermentation process to generate the energy that it needs to survive and to reproduce. All right, so that's the chemistry of brewing. Thank you for coming.
More beer.
The serving beer downstairs. Okay, it gets a little bit more chemistry involved than that, obviously. So it's a bit of a balance, right? So I'm a chemist. Many of the people in this room are either chemists or students of chemistry, and that's great to see folks out. But many of the people in this room are not, and so it's a bit of a balance. And I'm going to try to thread that loop if I can to provide some kind of interesting information for everybody in the room. There's going to be some chemistry because it is an American Chemical Society sponsored talk, so there will be quite a bit of chemistry involved. All right, so fermentation, we said, was sugar being used by yeast to form carbon dioxide and ethanol and energy, right? But this is not something that happens if you just take sugar and dissolve it in water. It doesn't form ethanol. I mean, you might say, I'm kind of bummed out about that. But on the other hand, it's kind of nice to know that when you put sugar out on the table, it doesn't spontaneously combust and form carbon dioxide and water, right? So sugar is a fairly stable substance. We don't tend to think that it's going to react like this to form ethanol, or that it's going to react to form carbon dioxide and water. But microorganisms like yeast, or larger organisms like us, we can go through this process of taking the sugar and converting it into these products and getting the energy out of it. And that has to be done in a very controlled, stepwise fashion. It can't be done all at once. We don't get anything out of it if it all happens at once. So what's happening is that these microorganisms, the yeast in this case, is carrying out this process in a controlled, stepwise fashion, one step at a time, collecting a little bit of energy from it each time. And it can only do that by having very specific compounds, chemicals called enzymes, which are a form of protein. They're a protein. And the enzymes are what carry out that process and allow that process to be carried out in such a way that the yeast can actually get something out of it. So to make beer, we have to have a couple of things. We have to have that sugar that is fermentable, that the yeast can actually use. So the sugar has to be there in a form that the yeast can make use of it. But we also have to have nutrients, and we have to have proteins for the yeast to use to do that, to go through that process. So I'm going to talk now. There's going to be some real chemistry involved. I'm going to show some chemicals, and it's going to be some sugar, and it's going to be some proteins. Sugar. Sugar is a combination, as I said, of carbon, hydrogen, and oxygen. This depiction of glucose is the sugar that we're most interested in here because yeast really uses the glucose. This depiction of glucose is in the ring formation, so it's 6 carbons, and the carbons are at any place that there's a joint in that ring, there's a carbon atom, okay? So there's 1, 2, 3, 4, 5, 6 carbons numbered on that screen. Those of you in the back must have much better eyesight than me to be able to read that, but they are numbered 1 through 6. And Each of those carbons is in a unique position in that molecule, and we talk about the different positions in the molecule by that numbering system. And then on each carbon, not each, but many of the carbons, there's an OH group, a hydroxyl group, an oxygen attached to the carbon. And the position of those oxygens and hydroxyl groups, but also the relative position to the ring, whether it's up or down, makes a big difference in the chemistry of the sugar and whether or not the yeast can actually recognize it. Yeast can recognize glucose because of the position of each of those hydroxyl groups on the ring. The one that's in green here, that's pointing straight down, that can be in either position. When that ring closes, it could either be down like that, or it could stick straight out. When it's down, it's called alpha position. When it's sticking out, it's called the beta position. And that's important for a few reasons. The sugar that we actually generate in the malting process and then in the mashing process in beer brewing is maltose. And it's two sugar molecules hooked together. And the first sugar, this is a glucose molecule here, is linked to the second sugar, another glucose molecule. The first position of this glucose molecule is attached to the fourth position of that glucose molecule. And the first position in this one is in the alpha position. So it sticks down like that. And they come down in a stepwise fashion like that. And that's the structure of maltose. And that linkage is called an alpha 1,4 linkage. All right. It turns out that starch, which is what we really have in the grain, we don't have maltose, we don't have glucose in the grain, we have starch. And the starch is a whole long chain of glucose molecules all attached together in this alpha 1,4 type linkage. So a great big long linear chain of glucose molecules attached together like that is a source of energy for the seed, and it's ultimately where we're going to get our maltose from and our glucose from for our brewing. And that long linear chain is called amylose. There's not going to be a quiz on the names of these sugars. But I will come back and tell you what the important things to remember from this slide are. But the long linear chain like that is called amylose. And it turns out that we can also have branches in the chain. We can have a glucose molecule at the 1 position, hook up to another glucose molecule at the 6th position, like is shown right here. And then we have branches in that starch structure. And that's called amylopectin. Okay? And it'll be important later, hopefully you'll understand why I pointed that out. The other thing is that glucose molecules can hook together with that oxygen here in that beta position. So there's more linear, and it forms a more linear structure like that. And the beta glucans like that are one form of cellulose. Cellulose forms the cell walls of plants. And those cell walls are actually very strong, okay, and very difficult to break down. So it takes, surprisingly, I mean, for a chemist, maybe it's more surprising than for a non-chemist, but for a chemist, these molecules don't look all that much different. They're all C6H12O6. They all have the same basic structure. They're all rings like this. They all have hydroxyl groups on the carbons. But it turns out that the enzymes that break these things down are very, very, very specific. And so the same enzyme that can break down starch cannot break down cellulose. Cellulose cannot be used by the yeast to make the ethanol. And it turns out too that even if you change the relative angle of those hydroxyl groups on that ring, it forms other sugars that the yeast cannot use. So that's how specific the process is in terms of which sugars can be used and what is useful for the yeast. This cellulose can get in the way of us in terms of making beer because it's there in the grain, it's there in the barley, and we have to break it down somehow because otherwise it's going to cause problems for us in the brewing process. All right, then there's proteins. Proteins, like starch, are a long chain of molecules all attached together. The difference is each of these little round circles here is meant to represent a small molecule. They're all attached together in a long chain in a very specific sequence. The difference is that instead of attaching sugars together in a great long chain, we're going to attach amino acids together in a great long chain. And those amino acids come in 21 different varieties. The difference is, the similarity is they all have an amine group, they all have an acid group, but they have some other group stuck on the side there that changes the chemistry of that amino acid. And it changes the chemistry of the protein as well. And so there's, as I said, 21 different amino acids, and they come as positively charged side groups. They come with negatively charged side groups. They come with really polar side groups that the water can solvate. And they come with really hydrophobic side groups that the water cannot solvate. And so what happens is when you start sticking all these amino acids together in a big long chain like this, some of those amino acids will start to interact one with another. And they'll hold the protein together in a very specific structure, a very specific conformation in solution. I know, it's really, it's really getting technical. And so, makes me want to cry sometimes too. So, what happens is that a protein, great big long chain of amino acids, it all folds on itself in a very specific formation. And that formation, that conformation of that protein determines its activity. This protein right here, and I don't worry about what all the squiggles mean and the floppy lines and all that kind of stuff. There's specific types of structures within a protein. But the protein is folded together in a very specific structure, and it has some calcium, has a calcium atom there, or ion, and a chloride ion in it associated with the protein. And that particular protein, alpha amylase, is the one that can take that starch and break it down into smaller pieces that we can use, okay? It'll only do that when it's in that conformation. So if I get the solution, if I have a solution of alpha amylase and I make it too hot, or I add the wrong solvents, or I put a lot of pressure on it, any kind of really difficult changes on the atmosphere of that amylase will change its structure and it'll change its activity. And ultimately, it'll become what we call denatured. It is no longer active, okay? So, the thing to remember from the carbohydrate slide, we have carbohydrates in the form of starch, we have carbohydrates in the form of cellulose. The starch carbohydrates we can break down, and we can use those for our brewing process and to make ethanol. The cellulose we have to get rid of somehow because it's going to cause problems if we don't. And then the proteins, we have to have the proteins there to carry out that process. And those proteins have to be in a stable form. We can't just do anything we want with our solutions of proteins and sugars. Otherwise, the proteins will fail to do their magic. Okay? All right. So, the process of making beer then. We start with barley. We start with a grain. And the barley comes in two different forms. It comes as 2-row barley or 6-row barley, which talks about how many seeds there are on the top of the grain up here, on either side. And the 2-row barley has a lot of the starch that we need. The 6-row barley has a little less starch and more of the proteins. Generally speaking, people are going to use 2-row barley to start with to make beer. We take that barley through a malting process, and I'll describe the malting process and some of the chemical changes that take place in that malting process to generate malt. The malting process, the maltster is typically not at the brewery, so that stuff is not being done here, but the brewery will be purchasing the malted barley and then using it to make the beer. Then the brewery will go through a mashing process to form what we call wort, which is a solution of the sugars, but also contains a lot of the proteins. We add to the wort the hops during that process, and we're going to boil it. And there's a reason for boiling it. There's a chemical reason for boiling it. There's also a biological reason for boiling it. After we boiled it, we'll cool it down. We'll add the yeast, and the yeast will ferment that to form beer, to form ethanol, and then some other things that we're not really all that keen on. So the green beer will then be stabilized and further refined to make the final product, the beer. Okay, so those are the overall process. We'll talk about some of the chemistry in each of these processes. So what is malting? We take this grain. If you take barley, if you take grains of barley, corns of barley, they'll call them, they're actually really, really hard. If you took that and tried to chew on it or eat it, it's really tough to chew down on. Think of grape nuts or worse. And but basically, it's really tough to break that barley grain down, okay? So that's not something that we can utilize very easily. What's in the barley grain? The outside of it is the husk, and that's not very usable for us, but it protects the grain. There's a embryo, which is going to generate the plant. And then there's the endosperm. The endosperm has a lot of starch in it, and the starch is there to provide energy for that embryo as it's generated, as it's germinating and producing the plant. Okay? And then there's other cells there which are important. They're not dead cells. They're dormant cells that can then be brought back to life and be allowed to produce a lot of the enzymes that we're going to need, a lot of the proteins we're going to need for this process. So we take this seed and we put it in water, and water can enter the seed through a small hole at the embryo end called the micropyle. And we go from dry barley, which is about 11%, 12% water, we'll bring that up to about 43 to 46% water. And what'll happen is the seed will then start to germinate. We want the seed to germinate, but we don't want it to actually form a plant. We want it to start to germinate, just the start of the germination, and then stop it. So why do we want the germination to start? Well, first of all, when that germination starts, the embryo and these aileron cells will actually produce the enzymes we're going to need for this process to get this thing to break down, to get that starch to break down into sugar that we can use. Okay? So those enzymes will be synthesized and they'll end up being distributed through that endosperm. We're also going to try to get rid of as much of that beta-glucan, that cellulose that I talked about on that sugar slide. We're going to try to get rid of as much of that as we possibly can. There are enzymes in the system which will break down that cellulose for us. Soften the grain so it's not so hard. And then we also want to break down, there's a lot of protein in this endosperm as well. Storage protein that's there, again, to provide protein and amino acids for that embryo as it starts to germinate. So we want to break those down as well. If we don't break those down, they'll end up making it through the entire brewing process, and they'll ultimately end up causing haze in our beer and unsightly visual for our beer. All right, and then we're going to generate amino acids as well. When we break down those proteins, we're going to generate amino acids, and the yeast is going to need those amino acids. All right. We've let it germinate, but we only let it germinate for just enough time to generate those enzymes, but not so long that the starch starts to break down. We don't want the starch to break down yet. So we want the enzymes to be available, but we don't want the starch to break down. So we're going to stop that germination by heating the kernels and drying them back out. And when we dry them out, the germination will be arrested. The enzymatic digestion that we were talking about, that's going to stop as well. And we can heat this to the point where we dry it out, but we preserve the activity of those enzymes. They don't become denatured. Okay? And we do that if we go to a lower temperature or an intermediate temperature in our drying process. So lower temperature will produce these light lager malts. Intermediate drying temperature will produce the pale malt that's used for almost all of the ales. And then we can also go to higher temperatures and generate these cooked or darkened malts, which have all kinds of interesting flavors that are introduced during that heating process. So we can go to very high temperatures in some cases to generate these really dark chocolatey malts that'll have coffee flavors and nutty flavors and all sorts of things. So the positive side of doing that is we get all those interesting flavors and that color, and we get the dark color that we can get in our beer. The downside is that we're going to denature all those enzymes. So if we just tried to make a beer with chocolate malt, we'd be in trouble because we wouldn't have the enzymes we need to generate the sugars that we need to actually get the fermentation to take place. So most beers, most ales are going to be made with a combination of pale malt, which preserves some of the enzymes, the enzyme activity, and then some of these other malts, which will give us the flavors and the colors that we're really interested in having in our beer. That color reaction, what generates the color, is called the Maillard reaction. Louis Camille Maillard, a French chemist, came up with this. Not too surprising that it was a French chemist who understood what happens when you cook things. But basically, it's a reaction between amino acids and sugars in the system. And we ultimately form these low molecular weight compounds, which give us a lot of different types of flavors and aromas that are important for beer. Okay, and we can get nut-like flavors, toasted flavors, malty flavors. We can get coffee-like flavors, that sort of thing. All right, so that's a little bit of chemistry behind the generation of the malt. We take that malt. The malt is actually delivered then to the brewery. The brewery, as I said, is not going to do the malting process, but they will start with the mashing process. And so they'll buy the malt, and they'll be very careful to buy malt that's produced in a very specific fashion to give them the flavors and the aromas and that sort of thing that they want in their beer. And then we're going to go through a mashing process. And so the mashing process is another physical process, but also a lot of chemistry involved. So the first thing we do with mashing, we take that grain, that malted grain, and we're going to steep it in water. And we're going to do that at higher elevated temperatures, and we're going to go through a temperature regime, you'll see in a minute, where we change the temperature over time. The purpose of this is, first of all, to gelatinize the starch. So starch is a solid material. It's pretty hard to, for any kind of enzymes to start to work on that starch. But if we get to high enough temperature, the starch will melt a little bit, and it'll be hydrated. It'll be in a more gelatinous type form where the enzymes have access to it and can actually break it down. And those will activate the enzymes during this mashing process so that they actually do break down the sugars. We want to degrade any proteins that are left in that endosperm. We want to break down any of the cellulose that's left, and then we want to break the starch down into a form that the yeast can use it. So we're going to convert the starch to maltose. The yeast is going to use that maltose to make, in the fermentation, to make our ethanol. And we're going to dissolve the maltose into a solution that we call wort. Okay? All right. So it's the water is a very important part of this process. So it turns out that the water you're drinking is probably more than 90%, the beer that you're drinking is probably more than 90% water. Some people have described beer as slightly contaminated water. Okay? So the water is important, not because water, I mean, all water is water. It's a small molecule. It's got a lot of fantastic properties that allow us to support proteins and dissolve sugars and do all these types of really fantastic things. But more importantly, it's the small, low concentration components that are in the water that make for the terroir of beer. Any kind of chemical or biological contamination should really be removed from the water before we do this process. We don't want to be adding microbes and bacteria, and we don't want to be adding a lot of pesticides and all that kind of stuff to our beer at this point. So we want to have clean, pure water. Okay? We're all familiar with a company that talks about the really pure Rocky Mountain water that they use to make their beer down in Golden, Colorado. Right? I have no problem with the water that they use. All right. Dissolved in that water, one of the important components dissolved in the water is calcium. Okay, we are familiar with calcium being dissolved in our water in terms of water hardness. There is either carbonates or sulfates in the water. We report it as, amount of calcium carbonate in the water. It turns out there's not a lot of agreement between brewers as to how much calcium should be in water or what the right concentration of calcium should be. Ales were originally brewed in England and in places like Burton-on-Trent, where the calcium in the water is really high, 350 parts per million, we call that. It's a high, just take my word for it, it's a high concentration. So some brewers will actually go through a process they call Burtonization, or they will Burtonize the water to bring the calcium concentration up to that level. On the other hand, lagers, pilsners, originally brewed in places like Pilsen, the calcium there in the water is very, very low. less than 10 parts per million. Okay, so a lot of times brewers that are trying to brew these traditional lagers and pilsners will actually try to reduce the calcium level in their water through ion exchange to get the calcium down to lower levels. Calcium, well, I mentioned it, it's in that structure of alpha amylase that I showed you. So it's important for some of the enzymes. Calcium reacts with phosphate in water to make the water more acidic, bring the pH down. It'll precipitate oxalic acid, and if we don't get the oxalic acid out of our system, it can actually cause problems down the line in terms of distribution of the beer. And then it'll also promote flocculation of the yeast. So as the yeast grows, it's going to ultimately flocculate, combine, come together, and either float to the top of the container or sink to the bottom of the container as the beer is being fermented. All right. A lot of brewers are very concerned about the so-called chloride to sulfate ratio, so chloride ions versus sulfate ions in the water. Sulfate is claimed to increase the dryness of a beer, whereas chloride is said to mellow the palate and impart fullness in a beer. You don't want to have a lot of iron dissolved in the water because that iron will lead to a metallic character in the final beer product. And then at some point, you do need to have a sufficient quantity of zinc in the system because the yeast requires zinc to generate some of the enzymes that it's going to use in the process. All right, so what's involved in mashing? First thing we're going to do is take that malted barley and we're going to mill it. Most of the time it'll be milled down to a point where there's still some fairly coarse material from the husks because we're going to use that coarse material to filter everything out of the mash when we're finished. In some cases, though, it can be ground all the way down to like a flour-like consistency, and then we'd have to have some other type of filtration process to get it out of the wort. The milled malt is mixed intimately with the water, as I said, and we're going to make sure that we have the right ions in that water, and we're going to have a pH somewhere between 5.2, 5.6, that means slightly acidic pH. And then there's several steps in the process. We'll go through a rest stage where we heat this mash to about 113 degrees exactly. Why does it say 113? Because I converted it from Celsius degrees. Okay, so it's about 110 to 115 degrees. We want to heat this water, heat this mash. And what we're going to do there, those cellulose molecules that were in that mixture, we want to try to break anything that didn't get broken down during the malting process. We want to break it down here into smaller sugars. Any cellulose, any large cellulose-like molecules that make it through the brewing process are going to increase the viscosity of the wort, increase the viscosity of the beer, and cause problems for us. So we're going to try to get rid of those. We can't go to too high a temperature because the enzymes that break down the beta-glucans, the cellulose, those enzymes are not stable at high temperature. So we have to stay at relatively low temperatures in this stage. We also want to get rid of the last of those proteins that might have been left behind with the starch in that endosperm. And again, the proteins, the peptidases they're called, the enzymes that break down the proteins are not stable at higher temperature. So a lot of times it'll be raised to this intermediate temperature and held there for a while to allow those processes to take place. And then we'll gelatinize the starch, it's called, and that's at 149 degrees for, let's say 150 degrees Fahrenheit, for starch from barley. If we wanted to look at other grains, and a lot of breweries use other grains besides barley, the gelatinization temperature for those grains is usually higher than that for barley. And so we'd have to go to a higher temperature cooking for those grains and then add them into the mash afterwards. All right, and then we're going to convert the starch into maltose. Maltose is the sugar that we really want. But remember I said that starch has those branch points in it? So what's going to happen is we're going to break that starch down into maltose using two different enzymes, alpha amylase that breaks the starch in the middle, And then beta amylase, which comes along at the end and takes 2 glucose molecules off at a time to form maltose. But there's no enzyme in this system which will break down those branch points in that starch. Remember the amylopectin I talked about? We're not going to break down the amylopectin. And that can represent up to 20% of the sugar that's there. And so what happens now is that we're getting a lot of maltose from our starch, but we're also getting a certain amount of sugar that the yeast is not going to be able to use. It's not going to be able to recognize those branched starch molecules. So we get some dextrins that come out of this that we're not going to be able to break down. Those branched dextrins, like I said, are about 20% of the sugar, and they end up in the final product of most beers. And it's not a bad thing. They contribute to the mouthfeel. They contribute to sweetness of the beer. Okay? It is a bad thing if you're trying to make light beer, right? If you're trying to make low-calorie beer, you don't want a lot of sugar left around in solution. So you got to get rid of that somehow, right? I don't imagine there's too many of us in here worried about making light beer, but there are people out there that sell a whole lot of light beer, right? It's the major part of the American market is light beer. And so what has to be done is to either digest or somehow otherwise remove those branched dextrins from the beer. And you can digest them, break them down into smaller sugars, and that can be utilized by the yeast if you add exogenous enzymes, other enzymes to the process to break those sugars down. Okay. So there's a great big argument on TV at every football game. It's tastes great, less filling. I'm on the less filling side. Okay. Then we want to take that wort. It's kind of a messy mixture right now. It's got grains and all kinds of other stuff in it. We want to filter that out a little bit so that we can get down to where we have a nice, relatively clear solution called bright wort. And so that's filtered. A lot of times just the hulls of the grains are left and used as a way to filter the rest of the material out of the wort. All right, so now we've got wort, and what we have is a really strong sugar solution, lots of sugar in the wort that is mostly in the form of maltose so that we can utilize it, the yeast can utilize it to make the ethanol. And so what we're going to do is we're going to cook that wort, and we're going to add hops either at the beginning or toward the end of that process, or even later we can add hops. But we're going to bring the wort to a boil, and we're going to boil it for a couple of hours, an hour or two, okay? And this does a lot of things. This deactivates and denatures all those enzymes that we've been using all this time. All those enzymes that have survived through this process up until now, you start boiling things, they're going to be deactivated. They're going to be denatured. We're going to sterilize the wort. So for the longest time, when it was impossible to get good, clean drinking water, it was a lot safer to drink beer than it was to drink water. And this is in part for the reason right here, because we're boiling it, we're killing off those microbes that might otherwise make you sick. Going to coagulate the proteins. Anybody that's ever boiled an egg knows that if you take protein and get it that hot, the proteins will coagulate. There's certain proteins that have survived through this process to this point that we don't really want in our final product because they'll make the beer look hazy. Okay, so we're going to cross-link proteins with tannins or polyphenols that came from the malt, and we're going to be able to remove those proteins then. We're going to extract and isomerize the resins from the hops. So the hops have resins on those buds, which give us the bitterness in the beer. And so we're going to be able to extract those, but also isomerize those, and I'll tell you what that means in just a second. We're also going to, during that boiling process, drive off a whole lot of compounds that we don't want, things that smell bad, that taste bad. They're going to go away during this boiling process. And we're going to increase the color of the wort because we're going to have a lot of these same kind of Maillard reactions taking place. So now we're adding hops to the system. Hops, the species is Humulus lupulus, and that genus Humulus is in the same family as marijuana. Okay? to my knowledge, I've been told that the resins in marijuana have certain hallucinogenic properties or whatever. But as far as I know, the resins in hops do not have those properties. These were first recorded to be grown in Germany in 736. So that's probably a couple thousand years after people started making beer. And so there's a lot of different types of, there have been a lot of different types of herbs and other compounds that were used to cut the sweetness of beer before people started using hops. It took England about 700 more years to figure out that hops were a good thing. And it turns out also that there are essential oils in the hops that can provide that aroma that we really want in our beer. The resins provide the bitterness, but also they are antimicrobial. And there's a lot of varieties that provide different ratios of those essential oils to the resins. All right. I told you I would tell you about isomerization. So basically the resins show up in the hops as these alpha acids. And as we go through this heating process and boiling process, they're converted, they're isomerized into these iso-alpha acids. And those iso-alpha acids can be dissolved in the water, and they provide the bitterness to the beer that we really want. We can also add hops late in the process. So we add hops and boil them and isomerize them, but we can add hops late in the process. If we add them early in the process, those essential oils, those aroma compounds that we're really interested in, they're all going to get driven off during the boil, and they're going to disappear, and they're not going to be there. So we'll add some hops. We can add some hops late in the process toward the end of the boil, or in England, they even do something called dry hopping, and people in the United States are doing this now too in microbreweries, where after the boil is completely over, the hops are added at the very end of the process. All right. Hops are a great thing because they provide that bitterness that some of us like, some of us don't. And then they do cut the very sweet flavor of beer that would otherwise be there. They provide those antimicrobial properties, but at the same time, these alpha acids are actually responsible for that property in beer that we describe as skunkiness. So what happens is that these iso-alpha acids, in the presence of light, will be broken down into smaller compounds, which will ultimately form this 3-methyl-butene-1-thiol. Thiols are not good things, okay? They're stinky compounds. And this is not the compound that's found in skunk spray, but it does give that same kind of skunky odor. Right? So that's not a good thing. We don't want this to happen to our beer. So the way to avoid this is to prevent it from being exposed to light. So put it in dark bottles, put it in a dark growler, put it in a metal growler where no light can get to it, and prevent the light from hitting it. Okay? That's easy, that's simple. But we have to market the beer. And if we're Corona or Heineken or Miller, we want to market our beer in clear bottles or green bottles, and the light still gets in there and it still causes this to happen, right? So how do we prevent that from happening? The marketing department's telling you, the brewer, that we're going to put this in a clear bottle. So what you're going to do is purchase hop extracts that have been stabilized against UV light. And so that if we can reduce those hops, those extracts rather, we can reduce these compounds by adding hydrogen in one way or another, or both ways, then we form a much more stable compound that does not break down in the presence of the light. Okay, so that's what some of these companies that are selling you beer well, they're not selling us beer, but they're selling some people beer in clear bottles, okay? That's what they're doing to make sure that their beer doesn't become skunky over time. Okay, so now we've gotten through this process. We have a wort which has the resins in it, has the iso-alpha acids in it. It's ready to be fermented. We're gonna have to cool it down to lower temperature if we're gonna use lager yeast, or slightly higher temperatures, we're going to use ale yeast. We're actually going to oxygenate the system. This is the one time in the whole process where we're going to actually add some oxygen to the system. Most of the time we're going to try to keep oxygen out as much as we can. We're not adding oxygen so that the yeast can respirate. We're adding oxygen because yeast needs some oxygen to form the lipids, to form the cells. And so it needs to have some oxygen to produce and to survive. We're going to measure the specific gravity, the density of the solution. We want to know how much sugar is there because that tells us how much ethanol we might be able to produce. And we're going to maybe add some additional nutrients for the yeast to work with. All right. Yeast. I told you yeast is the hero of our story. It wasn't until the 1800s that anybody understood that yeast was actually a living organism. People have been making beer for thousands of years, right? And they've been taking yeast out of one batch and moving it back to the next batch to produce the next batch. Back slopping, they called it. People knew they had to do that. It was some kind of magic, right? And it worked. In the Middle Ages, they called it God is good. It means exactly like it sounds. Okay. In 1680, a Dutchman, Antony van Leeuwenhoek, he looked at yeast for the first time under a microscope. Okay, and it was in the 1830s that a Frenchman and two Germans reported that it was actually a living organism, and they were basically taken to the woodshed for it. They were told that this is just nonsense. It cannot possibly be the case, okay? And then Louis Pasteur came along and said, yeah, actually it is, okay? Yeast is a living organism. And not only did he say that, but he said, after you've fermented the beer, if you really want yeast, you really want the beer to have a long life and not go bad on you over time, then you ought to pasteurize it. You ought to heat it up and kill any other microorganisms that are existing in the yeast, in the beer at that point. And major manufacturers still pasteurize beer. Okay. All right, there's two types of yeast that we generally use. Lager yeast, Saccharomyces pastörianus, works at a lower temperature, and it drops to the bottom of the fermenter as it coagulates or flocculates after the fermentation process. Ale yeast, Saccharomyces cerevisiae, I don't know how to pronounce that, 64 to 72 degrees, higher temperature, kind of room temperature fermentation. Tends to form more flaval volatiles and esters, the types of things that a lot of us like to enjoy in our beer. And it will rise to the top after flocculation. If you ever are looking at this and trying to take a quiz, Pastörianus, look at the last four letters of that word. And remember that that's the bottom of the fermenter. Okay. And then there are a lot of different strains of yeast available to us. These are two species of yeast. A lot of different strains within those species, and each of those strains produces different types of flavor compounds and different types of components. And there's even wild yeasts. You can leave your brew, leave the wort open to allow it to collect wild yeast from the environment, and that'll form wild ales, all kinds of interesting flavors. All right, so we said we get yeast in fermentation. We said that was the chemical process. It's a little more complicated. I'm not going to go through this in great detail, but I want you to know that there are a lot of different types of compounds that are formed by the yeast, and the different strains of yeast will produce different levels of different secondary metabolites, we call them. These esters are important for flavor and aroma. These fusel alcohols, larger alcohols, the same sort of thing. Then there's a compound diacetyl. Nobody wants diacetyl in their beer, okay? It's produced during the metabolism process. It's produced as a side product of the formation of amino acids for the yeast. And diacetyl gives awful flavors to beer. No worries. So the sulfur dioxide that forms can be a good thing. It suppresses some of the off flavors and it serves as an antioxidant for beer. Acetaldehyde that forms during the regular fermentation process and is ultimately mopped up in the fermentation process. If it's left behind, will give a green apple flavor that people don't really appreciate in beer. These esters and alcohols will give these flowery, fruity notes that people do appreciate in beer. And then diacetyl gives that butterscotch, buttery, off flavor note that nobody wants in beer. And it doesn't take very much diacetyl. Even very low concentrations will give beer an off flavor. Fortunately, the yeast does mop up the diacetyl at the end of the process. It forms this diacetyl, and then it will actually oxidize it, or actually reduce it, to a diol. So, and that doesn't have the bad flavors. So you need to run the fermentation process long enough to use up all the acetaldehyde and form ethanol, but also to allow the yeast to mop up that diacetyl and get rid of the diacetyl in the solution, because if it's there, it's going to give your beer an off flavor that nobody enjoys. I should say there's a lot of different processes out there that are available to try to get rid of diacetyl after the process, including the addition of exogenous enzymes that will take care of that diacetyl for you. Okay, just one small example. The flavor of beer is made up of, an aroma of beer is made up of hundreds of compounds. So one small example here and just how complex it is to think about what's going on with just one small molecule. We start off with an amino acid. We heat it either in the kilning process or in the boiling process of making that wort. And it will generate this dimethyl sulfide. Okay? Most chemists in the room are going to say, we don't want dimethyl sulfide in our beer. But it turns out that dimethyl sulfide is a fairly significant character note in a lot of German lager style beers. And it's there in fairly high concentrations in Rolling Rock beer. Okay? So that'll form. If we boil the wort long enough, we can get rid of a lot of it because it's volatile, it'll boil off and it'll disappear. We don't have it. Additionally, during the kilning process, in the presence of oxygen, it can form dimethyl sulfoxide, something else we don't really want to have in the beer. But after the dimethyl sulfoxide forms and during the fermentation process, the dimethyl sulfoxide can be converted back to dimethyl sulfide. So there's a lot of transformations, a lot of chemistry going on with just one small molecule that's adding to the flavor of particular styles of beer. All right, after fermentation, when do we stop it? We stop it when the diacetyl is gone, and we stop it when the specific gravity gets down to a level where we understand that most of the sugar has been converted into alcohol. All right? The specific gravity being the density again. Now we're going to separate the beer from the yeast. Unfortunately, the yeast kind of separates itself from the beer to a great extent. If it's a lager yeast, it'll settle to the bottom. If it's a ale yeast, it'll come to the top. But in some cases, we'll go through a filtration or a centrifugation process to get rid of the rest of the yeast. What do we do with that yeast? We can use it again. We can backslop, go back to the next batch, and add the yeast into the next batch. Be careful. Remember we talked about the different strains of yeast, and what happens to any living organism over time is that it evolves into different strains and might start to produce a lot of off flavors. So you can do that for several generations. Yeast is actually pretty stable, but not too many generations. Or if you live in England or you live in Australia, you can make a product called Marmite or Vegemite, which you're going to spread very, very thinly on your toast, because it has a very strong flavor to it, and it's actually, it's not an acquired taste. It's something you have to be born to believe in. Okay. If you're in the business of making lots and lots of beer and shipping it all over the country, all over the world, you're going to have to make sure it's stable and it's the same exact product every single time. Okay? We can make jokes about Budweiser and Bud Light all we want, but every time you buy a Budweiser, it's the same thing, right? It doesn't matter where you buy it. It's very consistent, and it's been stabilized and refined to the point where when it's shipped and you buy it at the grocery store, it's going to be the same product, okay? So all of us, anybody that's making beer, wants to get rid of oxygen at all costs. Oxygen will cause the beer to go stale. It's not exactly clear what the process is, but it is clear that the beer takes on a really lousy flavor, like cardboard. And so we want to eliminate oxygen from the beer at this point. We should have eliminated it during the boil, really, and it should not have been exposed to oxygen since the boil. We want to remove any of those proteins and tannins that are going to precipitate out. And so we can do that in part through cold conditioning, where it'll precipitate out a lot of those proteins. We're going to sometimes add things which will help us to precipitate those proteins out of the solution. We're going to filter it to make it nice and clear and be exactly the product that people want. One of the ways that we can get this cold break to form and to precipitate those proteins out is to use wood chips in the form of beech. So everybody's familiar with advertising about beechwood aging. The beech actually does allow the proteins to absorb to the surface of the beech. It's not usually chips, it's usually slats of beechwood that are dipped into the beer and then removed. We want to make sure there's no microorganisms, because anything that's growing in the beer is going to cause problems for us and for the consumer. So large companies will pasteurize their beer. There's flash pasteurization, where it's piped through pipes basically for a short period of time at high temperature, making sure there's no oxygen, because at that high temperature the oxygen is really going to be active and oxidize a lot of things. There's tunnel pasteurization. You can put the beer in the cans and then run it through a pasteurization system. There's cold filtering. So there's Miller and Coors that are both advertising that they never heat their beer, that it's cold filtered to get rid of the microorganisms. And then you must have to make sure that whatever you package it in is really clean and doesn't have any microorganisms in that. All right. It turns out that when we make beer, it's producing carbon dioxide, it's saturating the solution with carbon dioxide, and there's about 1.5 volumes of carbon dioxide per volume of beer, carbon dioxide gas were it all to come out. But the final product we typically want for the mouthfeel and for the flavor to have about 2 to 3 volumes of carbon dioxide. So that means we have to introduce carbon dioxide into the beer to make it carbonated. And that can be done in a variety of ways. It can be done by just straight introduction of CO2 under pressure. It can be done by having CO2 migrate across a membrane. Lots of home brewers, as well as lots of brewers in England, will either bottle or cask condition their beer, which means adding a little bit of sugar that the yeast can work on and form more CO2 under pressure and pressurize and oversaturate the beer with the carbon dioxide. All right, finally, we're there. We have beer. What do we want in our beer? What do people really look for in beer? It's really, of course, a personal thing. I mean, everybody has their own thing that they're really concerned about in beer. A lot of people are concerned about having foam, having this nice quality head on the top of the beer, and that they want that foam to last for a very long time. And that turns out, of all the times I've talked about it today, getting protein out of the beer, we need a little bit of protein at this point, because the protein actually helps us to form that, to stabilize those bubbles, that head at the top of the beer. Okay, there are other compounds from the hops that will also do that. Nitrogen helps, right? We can nitrogenate our beer, and we have nitro beers on pour. The reason nitrogen actually works better for head retention is that it has very low solubility in the water, in the liquid. And so it forms the bubble, but it doesn't dissolve and then go into forming another bubble and making larger and larger bubbles that eventually collapse. We like the color of our beer, so that depends on whether we use roasted malts or not, and the tannins, the polyphenols that were in there. We like clarity. Most of the time, people who are marketing beer are trying to market very clear beer with no haziness to it whatsoever, but there are, of course, certain varieties, Hefeweizen, New England IPA. These are varieties that are meant to be cloudy. They're meant to have a certain amount of haziness to them. And then, of course, we're interested in the flavor of the beer, unless, well, we're interested in the flavor of the beer. Okay, so what's the composition of beer? We're interested in how much ethanol is there. It's reported as percent alcohol by volume, and that's basically calculated from, we took that specific gravity measurement at the beginning, we took the specific gravity measurement at the end, we can do a calculation, we can look it up on a table, and we can tell you approximately what the percent ABV is for the alcohol. Or if you want to know more accurately, or if you have processes that may have changed that calculation, you can do it by gas chromatography. We can do that at the university, and we do that for some of the microbreweries in town. Bitterness is measured in international bittering units, and it's basically the concentration of those isoalpha acids I talked about. It has nothing to do with a flavor test for the beer, so it doesn't really tell you how bitter the beer is going to be. How bitter you perceive the beer to be will be a combination of how malty the beer is and how much of these alpha acids are in there. Okay, so it's a combination of those factors. Color, person can measure color with a spectrophotometer, but typically people are interested in having a beer of a particular color, at least it being the same color as it was last time you bought it. And then pH is typically in this acidic range for ales and for lagers. And then diacetyl we want to have to be at very low concentrations. Some people can taste diacetyl at concentrations as low as 40 parts per billion, which the chemists in the room know is a very low level. We want to consume it. Is it a good thing? Beer doesn't come with a label that tells us what the nutritional quality of the beer is, but in fact, it does have vitamins in the beer and folate in fact. Okay. I wish I could tell you the beer is the only place to get folate. There's lots of places to get folate. Beer does have calories, and people worry about the calories. People talk about the beer gut, and we'll talk about that in just a moment. I've been working on it for years. And then there's many, many studies out there based on various different types of diseases that show that the relative risk of death from a given disease depends on how much alcohol you consume, how much beer you consume. So this is units of alcohol per week, 7, 14, 21. 7 would be 1 12-ounce beer a day, 14 would be 2 12 ounces of beer a day. 42 and greater than 42, that's a 6-pack or more a day. It starts to get a little less positive out there. But actually there is a region in here where in many, many studies it shows that your health is actually improved. Your chance of death is actually less for various diseases if you consume beer moderately, 1 or 2 beers a day. Okay? These studies have done more to cause strife in various marriages than probably anything else. Okay. Are we out of time?
Oh, yeah.
Then I'll stop.
It's been awesome, though. The brewery has to stop serving
Okay.
at 8.
What time is it?
And it's really close. So
Okay.
about
Let's stop
20
then.
minutes.
I'll stop after this slide right here.
Yeah. What do you think?
And then I'll skip forward to a few other things.
Yeah.
But we talked about the calories in the beer gut. There's a lot of reasons to believe that it's not the beer. It's what people consume with the beer. While they're sitting on their couch doing nothing and watching television. And so things like chicken wings and French fries and pizza, many more calories than the beer. And so you're getting a lot of calories from elsewhere. All right, I'll stop. I want to go.